Hi, this is Sai Podana, founder at Embedded Systems AI LLC. In this video, I'm going to go over Transmission Control Protocol and its algorithms. TCP is one of the core protocols of the internet and operates at the transport layer of the TCP/IP stack. TCP is designed to provide reliable communication, ordered delivery, error detection, and congestion management. Unlike UDP, TCP guarantees the data arrives correctly in sequence and without loss. TCP establishes a logical connection between the sender and receiver before transmitting data. It supports full duplex communication, flow control, retransmission, and congestion control. Applications such as web browsing, email, file transfer, SSH, databases, and cloud services heavily depend on TCP reliability. Section 2 illustrates the famous TCP three-way handshake used to establish a connection. The client sends a sync packet containing an initial sequence number. The server replies with sync plus ACK, acknowledging the client sequence number and providing its own sequence number. The client sends an ACK confirming the server sequence number. After this exchange, both sides synchronize sequence numbers, allocate buffers, and establish a reliable communication session. This handshake ensures both devices are reachable, bidirectional communication is possible, and packet sequencing is initialized correctly. Unlike connection establishment, termination uses 4 steps because TCP connections are full duplex. One side sends a FIN packet indicating it has finished sending data. The peer acknowledges the FIN using ACK. The second side sends its own FIN when ready. The original sender replies with a FIN ACK. This process guarantees all outstanding data is delivered, both sides close cleanly, and resources are released properly. TCP's careful shutdown behavior helps prevent data loss and incomplete communication sessions. Section 4 shows the structure of a TCP segment. Important fields include source port and destination port. Both the ports identify communicating applications. The sequence number to track byte ordering. There is acknowledgement number that confirms received data. And there are some flags to control communication behavior. Examples include SYN for synchronization, ACK for acknowledgement, FIN for termination, reset for reset, PSH for push, and URG for urgent data. The window size field supports flow control. The checksum field detects transmission errors. Together, these fields allow TCP to provide reliable and ordered communication over unreliable IP networks. Section 5 shows TCP's sliding window mechanism. Instead of sending one packet and waiting, TCP allows multiple packets to be sent before acknowledgements arrive. The sender maintains a transmission window representing how much data may be sent without waiting for ACKs. The receiver acknowledges received bytes cumulatively. As the acknowledgements arrive, the window slides forward, allowing more data transmission to happen. Advantages include higher throughput, efficient bandwidth utilization, reduced idle time, and continuous data streaming. Sliding windows are fundamental for high-speed network communications. Section 6 talks about flow control. TCP flow control protects receiver from being overwhelmed by excessive incoming data. The receiver advertises an available buffer size called receive window or RWND. The sender limits transmission based on this advertised window. In this example, the receiver buffer gradually fills, causing the advertised window to shrink, eventually reaching 0 if the receiver cannot process the data quickly enough. This mechanism prevents buffer overflow, packet drops, and receiver congestion. Flow control ensures communication remains stable even when sender and receiver speeds differ significantly. Section 7 shows TCP congestion control algorithms designed to protect the network itself. Unlike flow control, which protects the receiver, congestion control prevents overload inside the network. TCP uses several major algorithms. Slow start. TCP begins cautiously with a small congestion window. The window grows exponentially to probe available bandwidth. Congestion avoidance algorithm ensures that once a threshold is reached, growth becomes linear to avoid sudden congestion. Fast transmit algorithm ensures that if multiple duplicate ACKs are received, TCP retransmits lost packets immediately without waiting for timeout. Fast recovery algorithm ensures that after packet loss, TCP reduces transmission rate gracefully instead of restarting completely. These algorithms allow TCP to dynamically adapt to network conditions. In section 8, a graph visualizes TCP congestion behavior over time. Initially, the slow start algorithm rapidly increases throughput exponentially. Once the slow start threshold is reached, congestion avoidance algorithm transitions to linear growth. When packet loss occurs, duplicate ACKs trigger fast retransmit followed by a fast recovery. If severe congestion occurs, timeouts reduce the congestion window dramatically. TCP continuously adjusts transmission rate to maximize throughput, minimize packet loss, and to maintain network stability. This adaptive behavior is one reason TCP scales effectively across the internet. To sum it up, TCP is one of the most important protocols in modern networking because it provides reliable delivery, ordered communication, error detection, flow control, and congestion management. Key TCP mechanisms include sequence numbers, acknowledgements, sliding windows, retransmissions, and adaptive congestion algorithms. Thank you.